Okay, so I welcome you once again to this lecture series on Introduction to Econometrics. In our previous lectures, we discussed about econometric methods. We also discussed about assumptions of CLRM, where we defined our linear regression model as a set of characteristics of a population that underlies a given, sample observations. The next thing that we talk about is estimating those unknown population parameters of the linear regression model that we have assumed. So if you remember in our last class, we talked about that we write the population linear regression function in matrix notation as y x beta plus mu, where y is a column vector consisting of n number of observations on dependent variable. X is your data matrix consisting of n number of observations on all such k number of explanatory variables. Beta is those unknown population parameters, and this mu is the column vector consisting of n number of observations on the error terms. So, our next aim is to estimate these unknown population parameters. There are several approaches through which estimation of these unknown population parameters are being done, but the basic starting point in econometrics starts with the method of least squares. This is what we'll discuss in today's lecture. So we discuss OLS, that is ordinary least square method of estimation procedures for estimating these unknown population parameters in today's lecture. Okay, so first we discuss about the algebra of least square, and then we go about intuitive part of why do we do this. So if we don't know anything about this unknown population parameter, the next thing that we can do is to have an estimate of these unknown population parameters. So let me write the estimate of these unknown population parameters as small b, and since we don't know we are using now estimators, so this error term will also be estimated. So let me write this error term as residuals, small letter e, and your y remains like this. So this e stands for residuals. This b is your estimators or estimate of these unknown population parameters. Okay, so algebra of least square क्या कहता है? Least square क्या कहता है कि I have to minimize the sum of squared residuals, right? So I have to minimize this term, residual term, and इसके sum को, square residuals के sum को we have to minimize. Now how do we go about this in vector notation? Let's see. So I can write this e as, let me write it. So I can write e as y minus xb, and in vector notation, if you have to write sum of squares, what you do is you simply take that vector and pre-multiply that vector with its transpose. So I write it as e transpose e. So y minus xb transpose y minus xb, right? E transpose e. So y transpose y minus of y transpose xb minus, now this is a product of transpose, huh? So AB transpose is B transpose A transpose. So XB transpose will become B transpose X transpose. So B transpose X transpose times Y plus of B transpose X transpose times XB. Right? Now focus your attention on this term, Y transpose XB. This is a scalar quantity. You see why? X is your data matrix consisting of n times k, that is n number of rows and k number of columns. B is your column of vectors consisting of estimators or estimate of those unknown population parameters. So B will have k by 1. So XB will have a product which will have a dimension n times 1, right? And then your Y transpose. So Y is a column vector consisting of n number of observations. If you take a transpose of this column vector, it becomes a row vector. So Y transpose will have a dimension 1 times n. So y transpose xb का dimension is n times 1. So 1 times n times 1 will become 1 times 1. That's a scalar, right? So y transpose xb is a scalar quantity. And one of the properties of a scalar quantity is if you take transpose of a scalar quantity, that is nothing but the scalar itself. So if I take transpose of y transpose xb, so this will become now this is a product. So A transpose B, right? So it can be written as B transpose X transpose, Y transpose will become B transpose Y. So Y transpose XB, its transpose will be equal to B transpose X transpose Y, which is nothing but equal to this term. So I replace this Y transpose X B as B transpose X transpose Y. So in the next thing we write as Y transpose Y minus of, now it will become 2B transpose X transpose Y plus B transpose X transpose B, and that's your this E transpose A is also called as residual sum of squares. In short notation it is known as RSS. So E transpose E is nothing but sum of square residuals, and this is the term that we obtain after this algebra. Now, what does OLS talk about? What we want to do is to minimize this residual sum of squares. So the general mathematical principles of minimization will tell me that I have to first obtain a first order differential and differentiate it with respect to unknown population, this variable beta, and equate it to 0. So next thing that we talk about is minimizing this residual sum of squares with respect to these beta. So how do we go about in vector notation? That's what the next thing that we do. So remember this term. Let me write this upper. So E transpose E is Y transpose Y minus of 2B transpose X transpose Y plus of B transpose X transpose XB. This is my term. And what I have to do is I have to take a differential with respect to these unknown population parameter. So you must understand this term Y transpose Y does not contain any term of beta B. So iska differential will always be equal to 0. Now look at this term. X transpose Y is nothing but a constant term because we have the data on X, we have the data on Y. So I can think of this X transpose Y as a constant. So this term is nothing but linear in this B, right? And look at this term over here. X transpose X will again behave as a constant because this is nothing but the product of the data matrix with its transpose, and we have the data matrix, that is we collect observations on the data matrix, so it becomes a known constant. So if X transpose X is assumed to be a known constant, so this term B transpose B is nothing but a symmetric quadratic form in B. So I can write this term as, so you must understand that a linear equation can be written as A transpose B can be thought of as A1 B1 plus A2 B2 AK BK, and this can also be written as B transpose A. It does not matter, where A are vector of known constants, right? Now if you imagine this A to be this X transpose Y, so this becomes the differentiation of del FB with respect to B can be written as del of A transpose B, or it can also be thought of as, right, differentiating this whole term. Now I can collect all these partial derivatives either in the row form or in the column form. But for the sake of the notation purposes, I write all these vector of partial derivatives in the column form. So differentiating this whole term with respect to b, and these are unknown, these are known constant, so it will nothing but your a only. So now you must understand, differentiating 2b transpose x transpose y with respect to b, will nothing but only this term multiplied by 2. So I write it as 2x transpose y. I repeat this again. This term x transpose y is a known constant, so this term can be thought of as linear function in B. A linear function can be written as in this form. So either you write it as A transpose B or B transpose A, it does not matter, as long as A's are vector of known constant. So if you differentiate this whole linear expression, either I can write in row form a1, a2, a3 so like ak, or I can arrange all these partial derivatives in the column vector. So a1, a2, a3 and say so on till ak. So ultimately if you write them in column vector form, this is nothing but the vector of known constant. Similarly, so 2b transpose x transpose y, if I differentiate this whole term with respect to b, I'll get nothing but this x transpose y, which is vector of known constant. So iska differentiation is 2x transpose y. Okay. Now next term is b transpose x transpose b. Now look at this term. If I think of it as a symmetric quadratic form matrix, let me write it as A. So this term becomes a symmetric quadratic form in B. Now why I am saying this, let me write it. So B transpose, let me write it as B1, B2, B3, A11, A12, A13, A21, A22, A23, A31, A32, A33. This is just to tell you that this is a vector of known constants. Sorry, matrix of known constant. My bad. So this becomes B transpose X, the matrix of known constant times B. Now if you multiply this vector and matrices, and I write it as expression terms, so what you'll get is as A11 B1 square, A11 B1 B1, so you must understand this, A22 B2 square plus A33 B3 square plus twice of, now terms will come, twice of A12 B1 B2 plus twice of A23 B2 B3 plus twice of A13 B1 B3. Now if you see, so this is my term. If I have to differentiate this term with respect to B, B is the vector, so B means B1, B2, B3 के respect में इस whole term को मुझे differentiate करना है. So if I differentiate this whole term with respect to B1, I'll just simply take example of B1 for the time being. So I'll get here 2A11 B1. I don't have B1 term here, so I'll have 0. Again, similar thing for this. Here I have B1, so I'll get 2A12 B2. I don't have B1 over here. Here again I have B1, so I'll get twice of A13 B3. If I take 2 common, so it can be written as A11 B1 plus A12 B2 plus A13 B3. Please don't lose your interest by seeing all these mathematical notation. They are very, very simple terms, simple matrix differentiation. And similarly, if you obtain differentiation of this term with respect to B2, you'll get the same notation. With B3, you'll get the same notation. So, this partial derivatives of the vector del f by del b1, del f by del b2, this can be thought as twice of, let me write it here as twice of a11 b1 plus a12 b2 plus a13 b3, twice of a21 b1 plus a22 b2 plus a23 b3, and twice of a13 b1 plus a23 b2 plus a33 b3. Now if you understand this, this is nothing but, the product of A times B, that is a matrix of known coefficients times your unknown population parameters or estimators in this case. So this is nothing but twice of A times B, where A I had considered this matrix form x transpose x. So its differentiation can be written as twice of x transpose xb, right? So इस टर्म का डिफरेंशिएशन आ गया आपको twice of x transpose xb, इस टर्म का डिफरेंशिएशन आ गया आपको twice of x transpose y. So let us move ahead. So differentiating this whole term gives me twice of x transpose y and twice of x transpose xb. The first order principle of minimization tells me that you equate this first order differentiation with respect to 0. So I write it as equals 0. So now it can be written as twice of x transpose xp equal to twice of x transpose y. I can forget these two from both the sides. Now this is a matrix. I simply cannot divide this matrix over here. So if I have to take this matrix this side, what I do is I pre-multiply both the sides with its inverse. So A inverse A is nothing but an identity matrix. So what I do next step is I pre-multiply both the sides by x transpose x ka inverse. So x transpose x inverse, x transpose x beta, x transpose x inverse, x transpose y. Now A inverse A is nothing but identity, so I can simply forget this. So your B becomes x transpose x inverse x transpose y, and this is nothing but your normal equations. Now the purpose of deriving this B through matrix notation is that the data visualization becomes clear. If you simply just write it in equation form, this data visualization is not clear. What B actually does, what B actually finds out is nothing but your all the observations from the data that you have collected. How it processes the information is nothing but this term. So we'll make sense with this term now. But before that, let us understand what is the intuitive part of OLS. So what does OLS talk about? So हमने लास्ट लेक्चर में ये डिस्कस किया था कि y can also be thought of as linear combination of these column vectors, right? And whereby linear combination, we have discussed that linear combination is nothing but a combination of two principal mathematical operations, that is addition and scalar multiplication of vectors. So idea क्या होता है OLS में, ये देखते हैं, and then we talk about this part. So ये इसको मैं ऊपर लिख देता हूँ so that you remember this. So your B is x transpose x inverse x transpose y. This is nothing but your normal equations. Now what does exactly OLS talk about is that if I have two vectors, so let's say x1, x2, just for the sake of simplicity I am taking this two explanative variables. So I have x1 and x2 as two explanative variables, and if I take linear combination of x1 and x2, any linear combination of x1 and x2 will lie in the column space of these two vectors. So let me write that linear combination part as, this is my linear combination, that is b1 x1 plus b2 x2 will be nothing but this term, linear combination. अब अगर y linear combination of x1 and x2 में lie करता है, then there is no need of error term. In fact, there is no need of econometrics as well. But what differs in econometrics is that we have an error term. That is, we cannot approximately understand the precise relationship between dependent variables and independent variables. So what happens is that actual y lies outside the column space of the linear combination of x1 and x2. So actual y lies somewhere here. So this is my actual y which lies outside. So अगर मैं सोचूं ये x1 और ये x2 है, any linear combination of x1 and x2 will be the floor on which I am standing. But my y actually lies somewhere here. That is, this lies outside the column space of the two exponential vectors that I have used, right? OLS क्या बोलता है that through appropriate estimation of those unknown population parameters, you reach to such point on the linear column space of x1 and x2 that is at the minimum distance from this y term. That is, through the various trial and error method, various estimation procedures, I must reach at such point of b1 x1 plus b2 x2 that lies exactly at a minimum distance. Minimum distance means if I drop a perpendicular, so perpendicular distance will be the minimum distance. So beta 1 and beta 2, finding out that those estimators of unknown population parameters is nothing but getting to that b1 and b2 value of b1 and b2, which takes you exactly at the to the point from which you can drop a perpendicular distance from this actual y. So this linear combination is nothing but your conditional regression. So I can write it as y hat, that is xp. So dropping a perpendicular, this is your error term. And exactly this is what OLS talks about. That is, you find out those values of b1 and b2, which takes you exactly to such point from where you can drop a perpendicular from the actual y values. This perpendicular distance is nothing but your residuals, and this is your estimated value of y using the data matrix. So this is the geometry of least square. Let us talk about now. I am sure you have understood this. So, let us make sense with this B is equal to X transpose X inverse X transpose Y. Please don't get discouraged by the notation that we have used. This is a very, very simple thing. So let me say that for two variable model, if I write X as 1, 1 consisting of 1, so I have n number of ones. And then I am using only one exponential variables. So x1, 1. Simply write it as x1, x2, select xn. I have only one exponential variable, so I am just writing in this form. Now, what is this term? X transpose x. So if you multiply this with its transpose, so iska x transpose kya hoga? 1, 1, 1. x1, x2, select xn. Right? Now, if you multiply this x transpose with x, what term will you get? So x transpose x will be so x transpose x क्या होगा? First row, first column, 1 into 1 plus 1 into 1 plus 1 into 1. This. So first element of this product will be nothing but number of observations that you have. So n. First row, second column, x1 times 1, x2 times 1, x3 times 1, x4 times 1, select xn times 1. So x1 plus x2 plus x3 plus till xn. So this is nothing but sum of all the values of exponential variables. So I can write it as summation x. Similarly, second row, first column will give you summation x. And second row, second column will give you x1 times x1 x1 square, x2 times x2 x2 square, say so on till xn square. So it will be summation x square term. So x transpose x is nothing but this n summation x summation x square. Okay? So please remember this. Now look at this term x transpose y. अब x ट्रांसपोज को हमने यहां पे देखा है 1 1 1, right? First row, first column, y1 times 1, y2 times 1, say so on till yn times 1. This is nothing but summation of y values. So I can write it as summation of y. x1 times y1, x2 times y2, so on till xn times yn. So this is nothing but summation xy, right? So this is your x transpose y. Now, you know, so x transpose x is n summation x summation x square. B is nothing but your b1 and b2, and x transpose y is this term. I'm sure now you understand this. It will be familiar with you if you write just in equation term. So these are your normal equations. N times b1 plus beta 2 times summation x is equal to summation y. Beta 1 times summation x plus beta 2 times summation x square is equal to summation xy. So this is nothing but the two normal equations that you have. Similarly, it can also be generalized for 3 variable, 4 variable and 5 variable and so on and so forth. But this b is a solution to your unknown population parameters. So b is equal to x transpose x inverse x transpose y. अब यहाँ पे एक बहुत ही important assumption का importance है यहाँ पे. I simply assume that inverse of x transpose x exists. If inverse of x transpose x does not exist, writing this will be, will not be justified. Now, when does inverse of x transpose x exist? As long as your x is that is all the columns of the data matrix are linearly independent of each other. Now, if you go back to your assumptions of CLRM, we had discussed that assumption number 2, that full column rank of data matrix. So, if the data matrix does not have full column rank, x transpose x का inverse exist नहीं करेगा और x transpose x का inverse exist नहीं करेगा, will not be able to write beta as this. So and that's why I had also told there that assumption is also called as identification condition. That if your x, the data matrix does not have full column rank, that is all the columns are not linearly independent of each other, you will not be able to identify the estimators, right? So that's why x transpose x inverse existing, why we are simply able to write this is because the data matrix consists of full column rank. That is, all the columns are linearly independent of each other. So I stop here till this point. In the next class we discuss about decomposition of sum of squares.